Hi, my name is Todd Austin. I'm from the University of Michigan, and this is an IEDM 2020 short course on memory for secure computing. In this course, we're going to be looking at what are the vulnerabilities that memory create and how can we stop attackers from penetrating those vulnerabilities. Who should be interested in this stuff? Well, basically everybody, if you're building hardware and system software, circuit design, etc. In fact, hardware designers are particularly important today from a security perspective for a number of reasons. First, hardware and system level solutions are needed to protect software and intellectual property. The lower you can get your protection technologies and the more immutable they are, because they're in hardware, the most immutable they can be, the more powerful those protections are. And hardware and low-level software support improves speed and quality of cryptography. And cryptography is expensive and it's used everywhere in security. So having hardware support for that is incredibly important. Hardware and software at the system level can most effectively seal up security vulnerabilities. As we'll see in this tutorial, this short course today, there's a variety of vulnerabilities that simple hardware fix can literally make go away. Rowhammer is a great example of one. And then finally, hardware designers that don't have a good understanding of security, they can create vulnerabilities that can be leveraged by clever attackers. In particular, as we'll look at today, side channels is one area where naive hardware designers that don't have good experience with security can run into a lot of problems in that they're creating these side channels. So why is security so hard to get right? It seems like every day we hear about more and more security attacks, and they fix them, and then they still got to fix them again. It seems like it's a never-ending wheel of attacks and fixes, and it has to do with the challenge of fixing security the way we do it today, which is really a patch-based approach. We wait till our systems are attacked, we analyze how those attacks work, and then we find and we fix those vulnerabilities. Often those vulnerabilities in software, sometimes they're in hardware as well. The problem is the complexity of hardware and software really outstrips our ability to look for security vulnerabilities. Manual verification of vulnerabilities is very difficult. And formal methods fall short because formal methods applied to security have to prove that something cannot happen. This graph's very interesting to look at. This is the number of lines of code on Boeing blue and Airbus red commercial airlines when their wheels leave the ground. And today there's about 50 million lines of code running on those systems when they take to the air. And it rises at roughly 2x every 4 years. Massive complexity. And given the number of bugs there are in that code, there's just so many vulnerabilities that can happen. In terms of hardware complexity, that is rising very quickly too. On this graph here below, you see the number of accelerators on the Apple SoCs in the iPhone from 2010 to 2016, growing very quickly from just 7 accelerators in the A4 to 37 in the A10. So the big challenge we have is how do we find and fix vulnerabilities before attackers find them? And that really requires formal methods, but that is difficult because we have to prove that something doesn't exist from a wide range of vulnerabilities, including vulnerabilities that have not yet been invented. Those are the hardest one to find and fix. And so ultimately we can't find and fix all those. So the trick to doing well at security is to always be engaged in it. It's an endless battle. And that what happens is we end up entering what's called the security arms race. And it's very difficult to escape this. But to not be in the security arms race really means that you're really building vulnerable systems. The way the arms race work is we build our platforms, we deploy our platforms get hacked, Our customers get upset. We then figure out how they were hacked, and we deploy countermeasures in software and hardware to stop those attacks, and the system becomes safer. And we once again go around this. The attackers then look for other vulnerabilities. And until we find that every last vulnerability, we're going to keep going around this circle. So really, vulnerability is not, it's not a destination, or excuse me, security is not a destination. It's a journey. It's an endless journey. And unfortunately, the way security works today, it really favors the attacker. Attacking is so much easier than protecting a system. That's because attacking requires only one known vulnerability, while protecting a system means eliminating 100% of the possible vulnerabilities in the system, which is generally very difficult to achieve in a complex system. This graph was made by about a decade ago by DARPA, a very interesting study that shows in the green lines here the growth of software used to protect systems from security attacks, things like network flight recorders, unified threat management, antivirus software, etc. And that was growing roughly 2x every year in complexity. And 2x every 2 years in complexity. And then here, this line, it doesn't really look like it's going up, but it's going up a little bit. This is the increase in complexity in malware over a 30-year period. Now, while the protections were growing 2x in complexity every 2 years, the malware grew 1.4x in size in 30 years. And that just shows you the challenge. The challenge of protection is a great one. We want to apply technology. We want to invest in security in order to provide security to our customers. And as a result, it seems like there's more and more security vulnerabilities every year. So we want to get on top of this. We want to educate ourselves. We want to leverage good technologies. And I think it's also helpful to understand, why do attackers attack? Why do they want to attack our systems? And there's a variety of reasons, and some we have some control over and some we don't have control over. In a large part, attackers want to control machines, not take them away or disable them. They just want to control them. They use this to create botnets. They also want to gain access to private information. This is a particular area of interest for memory attacks. They want to sneak out credit card numbers and keys so they can listen to what you're talking about. Another important area, which we do have some control over, is attackers will often want to punish and embarrass individuals and institutions. A good example of this was attacks on the Sony PlayStation that occurred after Sony decided they weren't going to allow Linux to be loaded onto that platform. Sometimes attackers work for good. An example of this is the Firesheep attack. This was a module that you could load into Firefox that would allow you to take over on an open network any social network that was being used without encryption. And the idea behind this was make it so easy to penetrate these unprotected streams to social networks that the social networks would actually go and add encryption by default. And that helped in that process of adding encryption by default. And then also attackers want to earn a reputation in the community. They want to show that they are, particularly adept at attacking systems. As designers, our goal is really what I like to call to win the bear race. There is no goal of having a 100% secure system. 100% security is like 100% reliability. It just doesn't exist. But we want to achieve a security stance that makes us less attractive to attack than all the other systems out there that could be attacked. And that's what I mean by winning the bear race. What does it mean to win the bear race? Well, there's the old story that you're out in the woods one day, camping with your friends, sitting around the fire, telling stories, and all of a sudden a giant bear pops out of the woods and starts running towards your group. And the question is, how fast do you have to run to not get attacked? Well, you have to run faster than the slowest person in the group, right? You don't want to be the slowest person in the group. In the security world, that means you're the easiest to attack. You're the most populated system. You're the most valuable to attack. Now, figuring out how much an attacker wants to attack a system, that's a pretty complex function. And some things we have control over, some things we don't have control over, some things we don't want to have control over, like population. We want to have big populations of our systems out there. The more systems there are out there, the more people are going to want to attack them. But we certainly have a lot of control over ease of attack. If it's easier to attack your system, people will. If there's really important things inside your system, they'll want to attack it. If people hate your company, they will want to attack your systems, et cetera. So it's a complex function, but we certainly do have control over how easy our systems are to attack. So let's take a look at the outline of this course today. First, we're going to look at some security basics. We're going to learn just some real basic information about cryptographic primitives that we need for the rest of the course. Then we're going to look at security exploits on memory. Then we're going to take a short break, and then we're going to look at techniques to secure memory, followed by future protections. And the goal here today, I just wanted to say, is not to give you all the information you need to identify vulnerabilities and protect your system. And no, the goal here today is to give you a roadmap on what the attack space looks like, what does the protection mechanisms look like, so that you can then start your journey to better understand all the particulars of attacks and protections. So let's get started with security basics. Of course, you need to learn about cryptography. Cryptography is fundamental technology in the area of security, and it comes in two primary varieties: symmetric key cryptography and asymmetric key cryptography. Now, by cryptography, I mean a mechanism where you can take unencrypted data, which we call plain text, send it through some fancy function that is parameterized by a key, and it renders what looks like pure random output. And that is the encrypted text. And we call that ciphertext. Now, with a symmetric key cryptographic function, an example is AES, DES, Blowfish, Cha-Cha. We can take that ciphertext, put it through the decryption function with the same key, and get the original plain text. Now, the plain text looks like the information we encrypted. They're the same. The ciphertext always looks completely random. And if we give it the wrong key on the output, the plain text that's produced also looks completely random. It's just garbage. Garbage in, garbage out. Now, the key about the key aspect of symmetric key cryptography is we have the same key on the input and the same key on the output. There's a number of modes that we can run our ciphers, as they're called, encryption and decryptions, in. The simplest mode is just a mode, it's called electronic cookbook, where we just take a piece of information and a key, send it through the cipher, and get the encrypted part out. The challenge with that is that's a really bad way to encrypt data, right? You can see in this picture here, we've got the Linux penguin, the original picture. And then what I've done is I've encrypted every pixel with the same key. And that's the ciphertext that I've arranged into the same picture format in the middle here. And you can see that, you know, when a certain pixel has a certain value, you get the same ciphertext output on the pixel. And you see there's these massive correlations between the input and the output. In fact, you can see that's the Linux pixel. You can see that's the Linux penguin, even though it's completely encrypted with a very strong cipher. This, by the way, is why DDR3 scrambling of memory is so easy to break. It's because they have these memory correlations, because whoever designed that system didn't understand that you have to really, you know, if you want it to be encrypted, you want to look like this. And the way you get this level of encryption is by operating the cipher in what's called a chaining mode. In a chaining mode, you take a piece of plain text, you encrypt it with a key, you take the ciphertext, XOR it with the next piece of plain text, encrypt it with the key, XOR it with the next piece of plain text, encrypt it, and then you do the opposite to decrypt it. When you do this, you then get this just completely random input. But there's a cost. There's a cost. The difference between the version of this without these edges, which is the example where you can see the output because there's no chaining, and chaining is, with chaining, you lose all your parallelism. And this is one thing you'll find when you build crypto hardware. There's no parallelism in it because everything is connected to everything else. That is the nature of cryptographic ciphers. And so to build them fast, we just have to build fast hardware. We've got to use very efficient logic. We got to drive it hard and, pack as much into a cycle as possible. One of the challenges with symmetric key cryptography is, let's say I want to send you a copy of my book that comes out next month, and I don't want anybody else to see it. All right. So I zip up my book and I encrypt it under a key, and then I send you the ciphertext via email. And then you say, what's the key? Oh, how do I send you the key? Well, I could just send you an email with the key. That's not very secure, right? I could send you the ciphertext with the key. That's really not secure. And that's one of the challenges with symmetric key cryptography. Since we both have to have the key, how do I get you the key without exposing it? I can't encrypt the key with the key. And that's really where the other mode of cryptography comes in, which is called asymmetric key cryptography. And this is a form of cryptography that uses what's called a public key and a private key. And it solves this problem of being able to distribute a piece of information even though you and I do not have a shared secret. I can get your public key. I can encrypt my secret with your public key, produce a piece of ciphertext that can only be decrypted by your private key. Now, your private key only you have. So I know if you get this plain text, you were the person that decrypted it. There's a few challenges here, like how do I get your public key? That's called certificate authorities. It's a little beyond this, but there's infrastructure in the internet to distribute public keys that we trust. Examples of asymmetric key cryptography algorithms are RSA, Diffie-Hellman. I'll just add as an interesting aside, these particular algorithms are built on what are called one-way functions. Probably the most common one-way function is factoring of large primes. So it's very easy to take two factors and create the large prime. Very hard to figure out what those two factors were. And so using that difficulty in one direction, we can make it easy to encrypt and make it very hard to decrypt without this extra piece of information, which is one of the factors. Quantum computers make those hard directions easy. And so things like RSA and Diffie-Hellman break. So when you hear about post-quantum computing, post-quantum cryptography, what they're talking about is asymmetric key cryptography, where that special function that allows you to build this public-private key system is built on a one-way function that no one has figured out how to break with a quantum computer. That's all that is. There are things like, run length errors, and et cetera, et cetera. There's a variety of things that companies like Microsoft make available today. Now, remember I said, if I encrypt a piece of data with your public key and you decrypt it with your private key, only you can see that piece of information. And using that, we can build a fundamental technology of cryptography called authentication, where we can prove to each other who we are. So let's say I want to take my browser and I want to connect to my bank. Okay. Well, what I can do is I can get a piece of information. I can encrypt it with the private key, my private key, for example. I give a piece of information to my bank. Let's go. So this is me, my little server. I'm sending you a piece of information, and I'm saying, hey, bank, encrypt this piece of information with your private key. Now, the private key is only held by the bank. That produces what's called a signature. They send that back to me, and then I decrypt that with the public key. One interesting aspect of asymmetric key algorithms, what is encrypted with the public key is decrypted with the private key. What is encrypted with the private key is decrypted with the public key. Now, if I can decrypt the message and get the same original thing that I sent to the server, that means that was encrypted with the private key. The only entity that can encrypt with the private key is the server itself. So I've now proven to myself, short of the server losing their private key, which they better not, I've proven to myself by seeing that original message again that I'm communicating with the private server. And that's how I can authenticate. For example, SGX uses technologies like this to do attestation of software. I can determine that a particular piece of software was signed by the developer of that software. Now, asymmetric ciphers are so powerful. Why don't we just use asymmetric ciphers and give these symmetric ciphers the boot? Well, the reality is that asymmetric ciphers are orders of magnitude slower than symmetric ciphers, and their keys are many times larger than symmetric ciphers. So think of asymmetric ciphers as maximally useful and capable, but super slow and huge keys and cumbersome to work with. Symmetric ciphers, on the other hand, we can make them run fast. They've got tight little 128-bit and 256-bit keys. So what we really want is algorithms that combine both of the benefits of these things for performance and capability. So let's just take a brief look at TLS. TLS is a protocol that you use when you connect HTTPS, the S means you're in TLS mode, to a secure web server. And what it provides is both authentication as well as high performance, what they call bulk encryption. So let's say I'm the client, I'm connected to my bank, the server. The client encrypts a private key that was selected by the client with the public key of the server, blasts that over to the server. The server then decrypts that with their private key using asymmetric key cryptography. Now, if that is not your server, then they can't decrypt with the private key of the known public key for that server. If someone else gets that message, they can't do this operation. Only the bank, as long as they haven't lost their private key, can do this operation. They then take the symmetric key out, they encrypt the word finished, and then send that back over to me. I take that original symmetric key and then quickly decrypt that. If that says finished, I know two things. I'm talking to my bank, and the bank has the right symmetric key. Boom, we're off to the races. And for the rest of this, we just do symmetric key, fast symmetric key encryption. So we always want to, you're going to see this in all systems. We're going to start with asymmetric, and then we're going to immediately shift over to symmetric key encryption once we've shared a secret. And then here's another thing you're going to find again and again everywhere in security. And so it's really something useful to know. And that's the idea of a hash function. A hash function is a function that can take an arbitrary amount of information, like Shakespeare's complete works, boil it down to a big value called a digest. Now that value is not unique with respect to that data, right? Because this is usually 256 bits and this is many gigabytes. But the probability that, that this value is equal to the hash of this and the original data that produced that hash is not this original information is 1 over 2 to the number of bits in the hash because of the distribution of the hashes over all the processing of data. What's also very interesting about this function is computing in this direction is really trivial. So taking a message, a big chunk of data, and producing its hash, trivial. Going in the other direction nearly impossible. In fact, the existence of being able to do that is essentially the death knell for the hash function. So you've probably heard of MD5. That's an example of a hash function. People figured out how to do that with lots of computing resources to go the opposite direction. What does it mean to go opposite direction? It means I give you this dead beef, bad food hash, and then you produce a piece of information that creates that hash. That means you can basically forge stuff if you know it's hash. SHA-1, SHA-2, you've probably heard of these. These are other hash functions. No one's figured out how to do that yet with any reasonable amount of computing. And so they're still safe hash functions. And this one-wave feature is really powerful. It's really powerful. Let me show you just a quick example of how we use it in everyday computing, the storing of passwords. Let's say you want to store a password. Someone gives you a password. You want to store it. Well, don't store the password, store the hash, right? Now, if you store the hash, when anyone gives you a password, you can just hash it, and then you check to see if the hashes are the same. Now, that's easy to do. That direction is easy. If someone hacks into your system and steals the password file, recreating the password is to go in the other direction. They have the hash. Now they have to start guessing words that might be the hash. And that's no easier than just coming to the login prompt and just typing random stuff and see if it works. So that's one example of where a hash comes in really handy in the crypto world. So that's the basics of computer security. Enough to get you started on the rest of the stuff. So let's take a look at some security exploits specifically on memory. Now, memory is a big part of every system. It's a complex component, often more complex than the main core. And it's that complexity that creates so many opportunities to get in there and find all kinds of information. With memory, we worry about both confidentiality. Can we keep secrets in memory and not let them get out? And we worry about integrity. Can people come in and mess with our memory? Can I get into that ATM and change my bank account value? So just a little bit of background about vulnerabilities. What are vulnerabilities and how do they create security exploits? Vulnerabilities are, in general, design bugs or naive approaches to design that create opportunities to sidestep around security measures. And I'm going to show you some examples of this. And they're everywhere, especially in software. Software bugs make so many opportunities to hack systems, both from the memory perspective and from the compute perspective. And they're in all systems. Of course, Microsoft Windows, Patch Tuesday, lots of bugs there. But even Linux has lots of bugs in it. Even IoT devices have lots of bugs. They've really become popular in the last decade for security hacks. So let's take a look at our first memory-based attack. This is a software-based attack, and this is the granddaddy of all security attacks. This was one of the very first invented and still an incredibly popular class of attack. It's called the buffer overflow attack. And it's a software attack because it leverages a software bug to basically manipulate critical memory components to change where a program will execute. So it's what's called a control flow or a code injection attack. We're going to basically take over the execution of a program, make it execute the code we want. How does it work? Well, you need a couple things. You need a buffer, a local buffer on the stack, and you need a read into that buffer, which goes past the end of that buffer. And then here I've shown the stack. I've got my buffer, some other variables, and then I got a return address. Now, if I read the right number of inputs, a well-formed input, then it fits within the buffer and everything's great. But let's say some clever hacker figures out that you don't check that it's only 256, and I give you more things. And then so what ends up happening is I write past the end of the buffer onto the local variables until I get this very special piece of memory here, which is the return address. And now the programmer has given me, the attacker, the ability to overwrite the return address in the current function. So you know what I can do? I can jump to my buffer and I can execute my buffer. I've now taken over your machine. What I've done is I've manipulated memory through a software bug, and I've taken over your machine. Welcome to the botnet. Here's another memory attack. This one's a little more physical and really plays on the implementation of DRAM. It's called a cold boot attack, and it literally uses cold to attack a system. The basic idea is you've got a DRAM memory in a system. You can see my DRAM memory here in this laptop. And the system itself has excellent security. And in that DRAM is things like the encryption key for the disk, maybe a network key, passwords, a variety of things that are well protected. That system is locked down tight. So what do? You take that DRAM and you move it from that system to another system without good security, and you just dump all the data. Now, we all know that if you pull DRAM out of system, the DRAM is going to discharge in a couple hundred milliseconds, and you're going to have to be pretty fast to get it to the other system, or you're going to lose all that data. But we also know that leakage is proportional to temperature. So if I supercool that DRAM, I can unplug it and I'll get maybe 30 seconds to get it into another system where I can then dump that memory. And inside there, I can find all your keys, your encryption key for your disk, and I can basically come back to that system with everything I need to hack it through and through. DDR3, for example, introduced what was called memory scrambling, a technique where you could basically encrypt the memory. But you can see how weak that encryption was. This is a painting that we put into that memory. One of my graduate students did this a few years back. And you can see the correlations between the data and the encrypted memory. That's encrypted memory on this side. That's not very good encryption. And so using these correlations, my student was able to basically reverse engineer the keys. He did it for DDR3. And then he did it again for DDR4. Even though DDR3 was known to have this problem, DDR4, all it did was sort of sort of made it harder to do this. Didn't get rid of those correlations. And so, strong encryption, like they use in Intel SGX, is really a good thing to start thinking about, because when you've got this much information leaking through your cipher text, it's easy for attackers to really reverse engineer what's going on in your system. Here's another great physical attack in a system that's really focused on memory. And this is the Rowhammer attack. It's only about 6 years old now. What it involves is leveraging crosstalk that exists between word lines in a DRAM. Okay. Here's the basic idea. I've got this DRAM, this two-dimensional RAM array. And let's say I own this particular piece of RAM, this row of the DRAM. And typical row of a DRAM will be, 4, 8 megabytes. It's a chunk of memory in my program. And then there's, I own this piece of RAM on the other side here. And so what I do is I start doing what they call hammering the RAM. I read that RAM, then I read the one below, and read the one above, and read the one below, and read the one above. And I do this repeatedly in such a way, that it creates crosstalk between what's called the victim line and the aggressor line. I'm controlling the aggressor line. The victim line has a slight amount of crosstalk on it. So as I'm hammering these two lines, the victim line is repeatedly getting little increases of voltage on its word line. And so it's getting proportionally increasing leakage out of its cells. And what you can do is, if you hammer hard enough, within a single refresh cycle, you can force those bits to reset and lose their data. And people have done all kinds of crazy stuff with this. It's like, oh, what can you do with this? Well, people would map page tables into physical memory and then row hammer them to point them to other pieces of memory. So now they've mapped their page tables into the user address space, and you can now own all of memory. You know, really clever stuff. Another attacker demonstrated that they could row hammer inside the Chrome sandbox, which is one of the tightest security mechanisms that we know of. But by row hammering the code, they were able to make illegal code, which could bust out of the Chrome sandbox. Really impressive stuff. And it just has to do with these crosstalks at the DRAM level. Difficult to eliminate, we'll talk about that later. People try to get rid of them, but we keep finding ways in. You know, you really got to be serious about stopping row hammer. We'll talk about some of those ways. And then you probably heard about this one. These were invented in or disclosed in January 2018, the Spectre meltdown attacks, and then all the stuff that went after that. These are what are called transient execution attacks that leverage cache side channels. So they're really blending a lot of different ideas together. We're going to look at some of these in detail. But what Spectre and Meltdown do is they basically use the misspeculation stream of a program. So what does that mean? That means I'm running a program, and the program is predicting branches, and for some reason, it predicted branches incorrectly. And so now I'm executing a piece of code that I should not. Now, that piece of code may be doing things that are illegal. Like one branch said, hey, you're not allowed to do this. Don't execute in this way. But I'm still executing that code because I've speculated on that branch. And so the goal of Spectre and Meltdown is when I get past those branches that I shouldn't go that direction, but the branch predictor got it wrong. And why did he get it wrong? Oh, because I cleverly trained the branch predictor to get it wrong. That's called priming. Now I'm executing a piece of code I shouldn't, but we always clean up. You know, we always clean up. You don't write the registers on the misspeculation path. But what Spectre and Meltdown do is they look at secrets in the program, they convert those secrets to cache line accesses, and the cache lines that are pulled into the cache are not undone after the misspeculation. And it allows someone else to infer information based on what cache lines were touched. It is a super clever attack. And I'm sure many of the companies out there that are dealing with it will attest to the fact it's really hard to stop. It's really hard. Why? Because there's so many of these side channels, as we're going to see in the microarchitecture. And we don't want to get rid of speculation. Speculation is guaranteed performance in our microarchitecture because we don't have to wait for branches. We don't have to wait for load store dependencies. We want to speculate. But when we do, we'll often execute code that's illegal. So anyway, it's a really rich area. It's kind of one of the hot areas of computer hardware security attacks right now. Everybody's attacking everything. Let's look at those side channels. Side channels are really an important part of hardware design because many of them come from hardware. And basically what a side channel is it's a way to look at a system and to examine characteristics of that system, which you're allowed to examine. Like, how much power is my system using? How long is it taking to compute this function? What's the electromagnetic radiation emanating off of my CPU? Maybe I can put some faults in the system and see how it reacts. I can undervolt it. Or, this is my favorite side channel, I'll just pay the administrator to tell me the password that I'll get in. That's called a social hack. But by looking at things like time and power and electromagnetics, I can infer information about what's going on inside. Let's look at one of sort of the basic side channel attacks, really difficult to get rid of. And this is a cache snoop attack, okay? A cache snoop attack. So what we're going to do is we're going to run two processes. And these two processes are on the same CPU. one process is going to ask the other process to do something. And when it does that thing, it's going to execute some code. And the code that it executes is going to reveal something about a secret. Maybe it's a cryptographic function. And when the key bit is a 0, it does one thing. When the key bit is a 1, it does another thing. And so what the first process does is it loads memory into its cache that overlaps with the same storage used by those two interesting pieces of code that the other program would run. And then I make my request to that other program. And then based on that secret I want to learn, either executes the first piece of code or the second piece of code. I don't know which one it's executing while it's running. But when it comes back, it will have displaced either one piece of my code or one piece of my other code. How can I tell that? Well, I just start executing that code, see how long it takes. Start executing the other code, see how long it takes. The one that takes longer was not in the cache. And so now I can know what that other program displaced in my code. And now that side channel, which is a conflict in the cache, has revealed through timing information about how that is working. And this sort of the classic cache side channels are, they do things like they look at RSA decryption algorithms, where in a sort of core, a poorly written RSA decryption algorithm, when you do this exponentiation bit by bit. And so they use the square multiply algorithm. So when the bit is a 0, you square. And when the bit is a 1, you square and multiply. And so the multiply is a different piece of code from the square. So what you do is you repeatedly load your code in your process that overlaps with the multiply. And then you look to see how often does it get displaced when I make a request to the RSA algorithm. The amount of reloading I have to do to this piece of code is proportional to how many times the multiply occurs in the RSA algorithm. Now I can know with some approximate number how many ones are in this secret key. And you'll know from probability and statistics that guessing a secret key with n bits is exponentially hard. But if I tell you how many ones are in it, it's basically polynomial. It's so much easier. So you definitely want to make sure that these side channels don't bite you. Fortunately, companies like Intel and AMD have put a lot of these crypto algorithms into dedicated hardware, the AES-NI core. And so they're not as side channelable up in that specialized hardware because they're not using shared memory. But these side channels really abound. And here's something really to consider. This is what really makes it tough. Look at what makes it easy to build side channels. Share resources, 1. 2, optimize the common case. 3, provide good visibility on the time it takes for your code to execute. And then ask yourself, what makes for a really high performance system? 1, share resources. So with the least number of transistors, you can maximize their utility. 2, optimize the common case so that you make sure that you're running your common operations as fast as possible. And 3, provide excellent visibility to the programmer on what is taking the longest time so they can optimize their code more effectively. So there is this fundamental tension between side channels and high performance system design. And escaping that is very, very difficult, very difficult. So now let's take a brief break, and then we'll be back to talk about techniques to secure memory. Thank you.